Thank you for having me here. So I'm going to talk a bit about image understanding, and in particular, I'm going to focus on semantic segmentation. So semantic segmentation consists in recognizing the objects appearing in an image and also to delineate those objects. So another way to look at this problem is by, so given an image, an input image, we want to classify each of the pixels among a set of classes. So this is an example of that. So first of all, one question would be, why are we actually interested in segmenting objects? So it turns out that it has many different applications, and I'm going to briefly talk a bit about a few of them. So one application is to help partially blind people, and this is actually one of the projects we are working on in our group. So for that, we have a special set of glasses that are able to project information in the glass, and then we use semantic segmentation to highlight the main elements of the scene. Another application where segmentation is useful for is to allow intelligent agents to interact with the environment. And that is useful, for example, for any kind of agents. For example, cars, automatically driven cars and drones. It is useful for that to recognize the area of the road, where trees are, where people are, and so on. And also, well, for robots in general to interact with objects in the environment. Different kind of application comes with different kinds of images. In this case, for example, we have medical kind of images. In this case, well, semantic segmentation have been applied, for example, to segment different kinds of tissues, like segmenting brain tumors and dental cavities in teeth. So, okay, we have seen that segmentation is useful for some things. Now the question is, how do we actually perform semantic segmentation? So, of course, we need to we start from convolutional neural networks because they are really they are great at learning good representation of images. But we have to keep in mind that semantic segmentation requires a very particular kind of output. So the output is structured. And therefore, convolutional networks by themselves may not be enough to get good performance. So starting from the beginning, we start looking at the fully convolutional neural networks. They were first described in this paper by Long and others in the context of semantic segmentation. This network consists in a set of layers, a set of convolutional and max pooling layers, followed by a set of deconvolutional layers that upsample the representation of the image back to the original size. So at the end, we have a one-to-one correspondence between the pixels in the input and the output. A similar approach was also developed by Hariharan, kind of simultaneously, and also related ideas can, in fact, can be traced back to the 90s in papers by LeCun and Benjo. So fully convolutional networks work really well, and at the time where they appeared, they became the state of the art in semantic segmentation in different benchmarks. But one issue that we saw is that the results that we get using this model are like the one that we see in here. So they present a poor object delineation. In the sense that, for example, in here we see that we have some meaningless blobs, and we are not quite able to recognize the shapes that are produced. So therefore, our objective here is to introduce this spatial consistency into our model. So in order to do that, we rely on conditional random fields. CRFs, they have been around for like 15 years, and they are useful for inference structured kind of outputs, which is particularly what we want to do here. They are based on minimizing a function like the one that we see here, where P is the prediction for all pixels in the image, and then the first term measure the predictions for each pixel independently, and then the important bit comes with the second term. So the second term favors smooth solutions, consistent solutions, by penalizing that similar pixels have different labels. So within the context of conditional random fields, there are many methods, many approaches that have been proposed. Here we focus on one that was developed by Graham and Colton. And roughly speaking, the purpose, the key point of this approach is that pixels that are, it favors that pixels that are close to each other and have similar intensity, similar colors, tend to have the same class, tend to be predicted using the same class. This is the algorithm that Graham and Colton came up with. So the first thing we did in our work is to express each of those steps as layers in a convolutional neural net. So let's start doing that. By the way, we have this I here below. It represents the raw image, the RGB image. Then we have Q is the current estimation of the pixels, of the predictions, and then U is the unitaries. So first, the first step in the loop, in the algorithm, inside the loop is message passing. This is a key step. This is where the predictions are propagated across pixels around, and pixels have similar intensity color. And this is effectively done by using a bilateral filter. Next, we have we weight the output of the previous step, and that can be done by using a convolutional, regular convolutional layer. Following step is the compatibility transform. At training stage, this step is able to learn how likely it is for two glasses to appear together. So, for example, sofa and airplane are less compatible than sofa and person, for example. So the model should be able to learn this in this step. Then we add the unary potentials, and finally there is a normalization there. So that is done by using a softmax layer. So this consists in, this is one iteration of the algorithm. We can put all this together in a conditional random field iteration. And one important point to note in here is that, well, the last 4 blocks, the last 4 layers are pretty standard in deep learning frameworks. It turns out that also the first one, the bilateral layer, is also differentiable. So therefore, we can do backpropagation through the whole pipeline. Now we can implement the whole algorithm we saw previously. First, the softmax, this is the initialization step that we saw before the loop. And then we see, well, we repeatedly do the iteration of the CRF, where we refine iteratively the solution until convergence. So because of this loop, this in here, this unit is a recurrent unit, and that's why we call this conditional random field as a recurrent neural net. Again, we can see that all the elements here are differentiable, so we can do backpropagation. Okay, so now we can put all pieces together. So we first started using a fully convolutional network. Then we take the output of that as an input to this conditional random field as an RNN. And we also introduce the original image into the CRF in order to calculate the bilateral filter. And finally, we get a prediction. So we have tested our approach against other different methods. And here is the results of some experiment. The approach in the left is the one that I have described before by Long et al. Is just using the fully convolutional network. The second one is by Chen and others. And what they do is to use a conditional random field as a post-processing method for the fully convolutional network. And then here is our approach. So the difference between our approach and the one by Chen is that we do end-to-end learning of the whole pipeline of the 2 blocks in there. So we think that that is important, or that is useful, because in that case, the weights that are learning in the fully convolutional network can be adapted with respect to the behavior of the second block, with respect to the behavior of the conditional random field, and vice versa as well. So the results that I report in here are, well, the measure is intersection over union, so the higher the better. And we can see that our method performs better than the others. So we have also implemented a demo, an online demo for this. I encourage you to have a look at that and try your own images. The demo and the implementation of the approach have been developed by Swaisen, Sadibya Yasumana, myself, and supervised by Torr. And in the following, I'm going to show a few examples that you can obtain with this. So this is a good example where the network performs really well, where it's able to segment several cats. This is another good example where it's able to segment different kinds of objects. But, well, the network doesn't work well. The model doesn't work well always. Sometimes it fails. One kind of mistake is when it classifies an object as something else, as it is the case in here, where the cat appears to be a bird. A different kind of error happens whenever the object is properly recognized, as it is the case in here, but the segmentation is poorly done. But these kind of errors are less common. Then, well, there are also other trick examples. Like, for example, in this case, we have a painting, and still we see that the network is able to do decently well. And this is another trick example, where it's a mixture between bird and dog and something else, and the network is able to do quite a decent job. Okay, so I would like to end talking briefly about instance segmentation. So far, one issue that I have omitted is that pixel level classification doesn't allow us to distinguish between different instances. So, for example, in the image that we see here, we see a set of votes. If we apply a segmentation model, a good segmentation model, we can get a solution like that, where blue represents votes, so it's correct. However, we cannot distinguish in the output how many votes we have, or whether different pixels belong to different votes. So because of that, we would like to get something like this as well, which is useful for counting the number of elements and treating each instance separately. So for that, we're using a different kind of recurrent neural net. So in this case, the main point is that the model is able to extract and to segment a different object at each time. So something like this. And so on until the whole image is completely segmented. So yeah, that covers pretty much everything I wanted to say. So the main points are that, well, we've seen that semantic segmentation is an interesting problem and it has many applications. We have seen that convolutional networks, fully convolutional networks, are a really good starting point, but they produce somewhat a coarse kind of prediction. We have seen that in order to improve over that, we have seen that conditional random fields are good because they introduce into the model the prior knowledge that pixels that are close to each other and pixels that have similar color intensity are likely to belong to the same class, and that is useful. And finally, we have seen that learning the whole pipeline end-to-end improves significantly the results. So thank you for your attention. I'll be happy to take questions.